Okay, this is Dr. Morton, and I'm going to record the lecture. This is for Friday, January 28th rather, Friday 28th at 10. And so I wanted to record it because today is the first in-person lab we're going to have for Micro 1 with 90 students. And I have to pass out the boards, and the lab starts at 10. Most days, when we meet in person, I'll certainly be there in person and everything. But today, I really wanted to do this. I want to be there in the lab at 10, and I can't obviously do a Zoom session at 10 and be in the Micro 1 lab at 10 at the same time. So I'm going to record this and cover this material, and just have you play it tomorrow at 10, and I'll send that out in a message, and I'll post it on the bulletin board. Well, obviously, if you're seeing it, you know. Okay, so anyway, so let's look at the syllabus, and we will, let's see, I want this. I don't know, this is crazy. Okay, so that's not what I want. I want this, and I can't find it. There we go. Okay, so I'm going to shrink myself down, and I'm going to put this back here. Okay, now, there we go. Okay, so here's the syllabus, and here's the 28th. And we're going to hopefully finish up Chapter 2. One of the things we'll talk about these alternate gate symbols and codes. I've talked about codes a little bit already, and I don't think I'm going to say much more about codes. What I do want to talk about, though, is the alternate gate symbols. And this probably will be a little bit shorter video as well. So we'll have a little bit shorter video today. I also want to point out here that I really want you to get your team, be thinking about getting your teams together. Actually, it's not a panic, but we can wait until you are in class and you can meet each other person to person and all that. But in any event, I do want you to be thinking about that. And as soon as we have our first week in class, assuming that we do, then we'll form the teams then, and then I can start kind of help you get kind of ready to do this as a team. But you won't. It's not actually due till after we get back from spring break. So we've got more than a month. We've got a month and a half, maybe even a month and 3 weeks. Okay. Notice as I've said to a number of you, but it's been kind of confusing. Okay, so I didn't even see I haven't met with the TA. I don't know if he couldn't find me today or what. Anyway, so I'm going to meet with the TA, hopefully tomorrow or early next week. I'm going to email him, and hopefully we'll get the TA engaged and doing the recitation section starting next week. And that's where we'll cover the homework. So don't worry about credit for the homework. Just go ahead and do the best you can. I know the homework disappeared from the book website, but they talked about taking a day to get it done. So hopefully it's back up today or will be tomorrow. I'm not going to look tonight, but I'll check on it tomorrow. Okay, but I do want you to do the end of chapter quiz by midnight tonight, end of chapter 2 quiz. And I'll take a quick look at that with you and maybe give you some hints at the end of this video. Okay, so let's move on. So what I'm going to do is I think I'm going to bring up this second video, and I hope I can make this work. Is that it? I don't think so. Oh man, no. Okay, oh, I see, I need this. Okay, see if this is the next one. Oh man. Well, the truth is, I obviously don't know how to use this program. Oh, it's video capture 2, that's the problem. Man, talk about confusing. Okay, here we go. Okay, there, and now we just need to do video capture 1. Okay, good. I think that's working now. Okay, and then I think I can expand this. Well, maybe not quite. Or maybe I can make this. I think I can do that. Okay. So, yeah. Okay, I think that's good. Yeah. See if this is right. I swear, there are times when I don't really understand how this stupid thing works. Okay, I think that's good enough for now. Hopefully this will work. Okay, and then I'm going to... Where is it? Oh, I see. It's called beneath here. Let's not pop too badly. Okay. All right. Okay. So, okay. All right. Okay, that's pretty good. All right. So, alternate gate symbols. Now this comes up in the book, and maybe I'll pop over the. Well, it's too much, too painful at this point. Oh man. Okay. All right. So here, what I want to do is just kind of we'll move from logic expressions to alternate gates, and this is just kind of getting us all ready. So remember, here's some things that we've covered. Okay, we've covered. The binary, math. We've covered number bases. We've covered the definition of digital and analog. We've covered precision. And we've covered accuracy. And we also touched on if it's precise and accurate, then it's valid. We've talked about codes, how we encode information, and we've also talked about the basic two input gates. Now, these gates actually can have any number of inputs, so they're not just two inputs, but we've really just defined them for two inputs. But the definitions for multiple inputs for all of them are pretty much obvious, with the exception of the exclusive OR gate, and it's not obvious what it is for multiple inputs. So maybe I'll just mention that in passing here in a minute. So I'll make a note. We'll come back to that. Okay. And then we've talked about truth tables and how they relate to our basic logic system, where we have some sort of network, and we have some inputs, and we have some outputs. We usually call these X's, and we call these say F's or maybe Z's, depending, or maybe Z's, one of the two. But the nomenclature is just arbitrary, but I'm going to use that throughout the course just so you can kind of know what to expect. Okay, so I want to say a little bit more about truth tables. So remember, truth tables basically define for some number of inputs what the expected output is. Now here's one of the things that causes a lot of confusion with students. And let's say we have a little truth table where we have three inputs, and we'll label these inputs A, B, and C, just for grins, and then we'll label the output F. All right. So we have 1, 2, 3, 4. 1, 2, 3, 4. So we're going to have 8 rows, and we're going to code it up. Like this, and I'm going to maybe draw some lines so we can keep track of it a little better. I'll pair the rows up, and so let's say our F here is, or we can do every individual row. That's fine. Maybe it's less confusing to do that. All right, and let's say we have some F. So 0, 1, 0, 1. 1, 0, 1, 1, 1, something like that. All right, so the first question is, where did we get this F? Now in this particular example, I just made it up, okay? So I just looked at it and said, let's just do this. So there wasn't any actual rhyme or reason for that. Okay, I just made it up. But in a general situation, or in a more, in sort of the generic situation, where do we get that? Okay, so where does this F come from? Well, this F comes from our customer. Okay, and I like to jokingly say we get it from God, because this is what we as the engineer are given. We're usually given it in the form of an English language statement. The customer will describe what he wants the system to do, and then we construct a truth table that represents that desired system. But it's based on what the customer wanted. Now, maybe a sophisticated customer would actually give us the truth table. That'd be great, because then we're going to go do the design work, and when we're done, if it's a simple design and it's just a combinational design, we're going to make sure that we have a network where if you give these inputs, you'll be guaranteed to get these outputs. So for this particular row, if A is 1, B is 0, C is 0, we guarantee the customer that F will always be 0. Now there's usually a small delay from when we first change our inputs to be this, before this is valid. And we call that small delay a propagation delay. Or we call it an inertial inertial I can't spell inertial, but anyway, it's an inertial delay. Not a very good speller. INIRTIAL, I guess. Anyway, so that's the inertial delay. This is the term that we use in Verilog, but a more generic term is propagational delay, and that's the one I usually use in this course. So we'll call these propagation delays or inertial delays. We also talk about transport delays in Verilog, and the inertial delays are the time that the gates take to change their outputs from low to high or high to low. But the transport delay is the time it takes for the signal to propagate down the wire through the switch matrix and get to the next logic element. That's at least in the case of an FPGA or maybe an integrated circuit. In any event, after some small delay, given these inputs, we guarantee that this F is going to have this output, and we're going to give you the tools so that you can design the circuit that will do that every time. And we'll even give you some tools that allow you to get to a near optimum solution for simple systems, and for bigger systems, then it's maybe more of a near optimum or a pretty good solution. Okay, so that's what we're going to do, and we're going to initiate. We're always going to do these things with gates, right? We're going to use gates. Now, when we take a truth table and we extract the information from the truth table to create this network that's going to give us the right output, we have a couple different ways to do that, and we're going to cover that in some later chapters after we learn a little more. This is going to make up the middle part of the course, and then our sequential designs are going to make up the last third of the course. So, but for the time being, what we're going to say is that we have tools that allow us to do this. That given this information, we can make a network that will give us this guaranteed result with a small propagation delay, because everything takes some time. There's always a teeny lag, although in the digital world it's really, really short, on the order of a few nanoseconds. But still, maybe 20 nanoseconds. But that's pretty fast. That's really quick. An example of that is, how long does it take electricity to go, if you have a wire that's say 1 foot long, about how long does it take for an electrical signal to go from one end of the wire to the other end of the wire, traveling at the speed of light, roughly? And a rough estimate is it's about 1 nanosecond. So you can see, if you're dealing with dimensions in the order of inches, then you can certainly have hundreds of nanoseconds involved. in the length of time it might take to go, say, 3 or 4 inches might be 300 or 400 nanoseconds. I mean, picoseconds. So 0.3 nanoseconds. So we do have to, in big systems with lots of connections, we do have to consider sometimes these distances come into play. In fact, frequently they come into play. So we have inertial delays and transport delays, I'm just going to generically refer to them as propagation delays, although strictly speaking, propagation delays are more associated with the inertial part, and those are usually the bigger part for our typical combinational network. Okay, now when we want to draw one of these networks, we usually first reduce it to a logic expression, and then we can modify that logic expression to get into the types of gates we actually want to use, and then we can actually build the circuit. For simple circuits, we can draw a schematic and actually breadboard it with discrete gates and do that. But for anything really complicated, particularly for big NVIDIA chips, we can't even make the schematic because it would take square miles for it for us to draw it out on a piece of paper. So we have to use design tools to do it. All right. So what I'm going to do now, so let me write a logic expression. Now I'm not going to explain how that logic expression would come out of this say truth table, but I'm just going to do it, and then later on you'll see how I did it. So this F then would be equal to A prime B C prime plus A prime B C plus A B prime C plus A B C prime plus A B C. Okay, so that actually is one way to express the solution to this truth table I just arbitrarily drew. All right. Now we can use switching algebra to simplify this. Once you learn switching algebra, that's going to be the next thing we're going to cover, or we could use a K-map, which we'll cover later on in the course when we start the middle part of the course. But we can simplify it. But for now, I'm just going to simplify it a little bit here. Let's see what would be a good simplification. So I'll maybe combine these two, and I'll get BC prime, and then we have ABC, so we can do plus BC plus AC. So I can simplify it to this for now, and I might even be able, I can actually simplify it more. I can simplify it to B plus AC. So here's the actual logic expression. But I think I'm going to use this one. So won't simplify it all the way. I'm going to use this one. All right. So let me draw this. This particular circuit, each one of these expressions here. So let me just rewrite it. BC prime plus BC plus AC. This is a logic expression. It has in this case 3 variables, A, B, and C. It has 3 terms, 1, 2, 3. Now it is also true that this whole thing is a term, but we don't usually count it that way. And then every appearance of one of the variables we call a literal. So it has 1, 2, 3, 4, 5, 6 literals. 6 literals. Okay, so that's the expression, and this particular expression is in 2 layers. Now I'll show you how it's in 2 layers right now. I'm going to draw it, and since this is an AND gate, I'm just going to draw an AND gate. This is another AND gate. We'll draw this one, and this is another AND gate. We'll draw this one, and these all are going to go into one OR gate. This one we're going to put in B and C prime. This one we're going to put in B and C. This one we're going to put in A and C as inputs. Each gate in this particular case is going to have 2 inputs, but it could have 3 or 4 or 100. Well, maybe not 100. the hardware probably wouldn't work with 100 inputs, but it could have more, certainly than 2. And then our output would be F. This circuit then will generate the F that we wanted in this truth table. For every possible input, this is the correct value that we would get out. We've specified it for, say, A is 0, B is 0, C is 0, F should be 0. And if we put that in to these gates, we will get that output for an F. Now, we can rewrite this circuit by using our alternate gate symbols and change it into one that only has NAND gates in it. And let me show you how we would do that. So the first thing we want to do is we want to go over the various gates. So let me do that. So obviously we have AND gates, and then we can have a NAND gate where it's got the inverter on it. We have an OR gate, and we can have an OR gate with an inverter on it. And then we can have we can also have an inverter, and we don't have an alternate for an inverter. And then we can have an exclusive OR gate, which we're really going to get to later. And then we can have the exclusive NOR gate with an inverter on it. So those are our basic gates. And as I mentioned before, we can add 2 bubbles, or we can combine 2 bubbles, and therefore eliminate them. And we can then slide a bubble on a wire from one end to the other. All right, so let's see how we can take this and use the alternate gates. So our alternate gates so here are our alternate gates. I didn't really do these, but for the AND gate, we just use an OR gate with bubbles on the inputs and the output. Now for a NAND gate, we just do the OR gate with just new bubbles on the inputs, but we get rid of the bubble on the output. And for an OR gate, we do an AND gate, bubbles on inputs and outputs. But for a NOR gate, we do just an AND gate with bubbles on the input and not on the output. And we're not going to worry about these. So those are our alternate gates right here. So let's use those alternate gates, and let's redraw this circuit. Let's see. I have to put this under. Okay. We might need to slide this down just a little bit. All right. So I'm going to do the alternate gates over here. So what I'm going to do, I'm going to put the OR gate in here. And okay, I just redrew it because it was getting a little messy. So now I'm gonna put in the alternate gate for this OR gate here. All right. So we're gonna leave the AND gates just like they are, but I'm gonna swap this out. So I'm gonna have 3 AND gates still. But my OR gate, now I'm gonna put an AND gate, and I'm gonna put bubbles on the inputs and on the output. And we'll still have BC prime, BC, and AC. Now what I'm going to do, I'm going to take these bubbles here on the inputs of this. Now it's an AND gate. Well, it's an AND gate because it's got a bubble on the output. And then here's F. I'm going to slide these bubbles up here so that what we'll have then is we'll have 3 AND gates, but we'll make them into NAND gates because we'll slide those bubbles up. We'll still have BC prime, BC, and AC. And then these will go down into one AND gate with a bubble on its output. And now we've gone from an AND OR configuration in 2 layers. So here's our input layer, layer 1, and here's our output layer, number 2. we've done the same thing. We still now have two layers, input layer number 1 and output layer number 2. But now it's in NAND form. Now, what's interesting is I can get it to NAND using this technique, but I cannot get it to NOR. To get it to NOR, I have to start with a slightly different arrangement. I have to have a network that starts with input OR gates and a one output AND gate, an OR AND configuration, and then I can go to the NOR. But you see how I could do this by changing this gate using an alternate gate and sliding the bubbles, and voila, I have NAND gates. Now later on we'll show you how to do this with switching algebra, but that'll be later on in the course. But same idea. Okay, all right, I think that's enough of the alternate gates. So I think what I'm going to do, is basically, I think I'm going to stop with this one. See if I can make myself make it bigger. Yeah, and I just have to. Yeah. All right. Yeah, and I'll go ahead and turn this off, I think. Okay, so I think I'm gonna sort of quit with that. Let me just I want to make sure we've covered everything in chapter 2. So hang on one second. Okay, so let me do that. That's display. I think we just have to do this. Yeah, and then I'm gonna. Okay, I don't want to do that. I don't know why it does that every time I do that. So, then we need to shrink this down. Okay. All right. Okay, so here's the book, and here are these alternate symbols. So just take a look at this, and all we did was substitute we substituted this symbol in for the OR gate to convert that from a AND OR configuration to a NAND configuration, and then we just slid the bubbles back up to the AND gates and turned them into NAND gates. Okay, and I think that's it. The one more concept I wanted to talk about was this concept of functionally complete set of gates. So functionally complete set of gates. So what that means is that if I have any logic expression, if I have a functionally complete set of gates, I can implement it with those gates, any logic function. So what are the functional complete sets? Well, so one functionally complete set is AND gates, OR gates, and inverters. That's functionally complete. But interestingly, and in 2 layers. But interestingly, I can implement any logic expression with just NAND gates, an input layer of NAND gates and one output NAND gate. I can also implement any expression with just NOR gates, one input layer of NOR gates and one output layer of NOR gates. And you can also implement it with exclusive OR gates. But we're gonna leave that because when it comes to manufacturing an integrated circuit, a NAND gate or a NOR gate is easier to manufacture than AND and ORs and exclusive ORs. So for that reason, almost all of our silicon is made with just NAND gates or with just NOR gates. And there may be some exceptions for line drivers and otherwise, but most of those gates will be identical things. They will just be exact duplicates of each other. And that again has to do with our discipline of regularity and uniformity. It makes it a lot easier to make the exact same gate over and over again, and each one has to be a little different. That's what we don't want to do. So you can imagine if you have something like 14 billion gates, the last thing you want to do is to have each one of them be a little different. That's a lot of different things. So, but if they're all identical, it's a lot easier just to replicate them. Okay, so that's the concept of a functionally complete set of gates. And I think with that, then let's look a little bit at the end of chapter quiz. And this is for chapter 3. Let's see, I think it's chapter 2 that's due. So let me go back to chapter 2 and we'll tackle that one. Hang on real quick. My scroll button depresses quickly. All right, chapter 2. And make sure you are reading through those. Okay, this was back in the number systems. And let me go all the way down to the quiz. Okay, so let's look at the quiz. And so I'm going to go through it here. We'll just talk about some of the things. Okay, so the first question is, convert 50 to an 8-bit binary number. Now you can use your calculator to do this, but I encourage you to do this by hand. So let me just work on this one for you a little bit to make it a little bit easier. So I'm gonna switch to the video capture, this one. Yeah, there we go. Perfect. Except I turned it off. But now it's back on, hopefully. Is that going to work? Oh man, I should have turned it off. Well, live and learn. Okay, well, yeah, I don't know how to fix that. Okay, maybe we can do the yeah. Okay, and then so we want to do the. Okay, here we go. Oh, that was the wrong one. Unbelievable. Okay, live cam. Okay, now we do. Okay, all right. Now we'll do this one. Video capture device number 2. Yeah, here. And there it is. And then see if that brings it back to life. No. Ah, that did it. Okay. All right. So remember, so we start like this. We take 2, we divide it into 50. That goes 25 times, remainder 0. That'll be the least significant digit. 2 into 25. So 12 would be 24. Remainder 1. 2 into 12 is 6. Remainder 0. 2 into 6, 3. Remainder 0. 2 into 3, 1. Remainder 1. 2 into 1, 0. Remainder 1. So there's our number, 0, 1, 0, 0, 1, 1. Now you know an even number always has to have an even value, a 0 value for the least significant bit, because that's the 1 bit. So count it up. So this counts for 2, 4, 6, 1, 2, 4, 8, 16, 32. So we add 16 and 32, that's 48 plus 2, 50. So it checks. Okay, so that's that one. We'll give you that one. Let's do a couple more. So we'll give you some hints. Convert 100101001 to a hex number. Okay, so remember, assume that the decimal point's here, and then divide it up into groups of 4, moving to the left. Pad with zeros on the left if you need to, and then convert each group of 4. So that's easy. And let's see. We're going to do this subtraction. I might just let you do that one. But remember, when you do it, let me do a different one. So if you do like a 1, 0, 0, 1, 0, and you're going to subtract, say, 0, 1, 1, 0, 1 from it. So 1 from 0 can't do it, so you have to take this 1 and you put a 2 here. 1 from 2 is 1. 0 from 0 is 0. 1 from 0 can't do it, so that makes it a 0. You put a 2 here, and then you borrow off from that 2. Now you have a 1 there and a 2 here. 1 from 2 is, oh yeah, we got to borrow that one too, so that's a 1, you have a 2 here. And then, no, sorry, this one goes with that. Never mind, we didn't need to do that. We're back to here. All right, scratch it. Let me do it over. 1, 0, 0, 1, 0, minus 0, 1, 1, 0, 1. Okay, I'm going to keep my numbers lined up now so I don't get lost. And, so let me... All right, so 1 from 0, can't do that, so that makes a 0 there. We borrow the 2. 1 from 2 is 1. 0 from 0 is 0. 1 from 0, can't do that. Can't borrow from here, so we borrow from here. That makes that a 0. 2 here, we have to borrow 1 from that, so that's a 1 and a 2 here. 1 from the 2 is 1. 1 from 1 is 0, and that's a 0, so a 0. So the answer is 5. And this would be 2 plus 4, 8, 16. So this is 18 minus 1, 5, plus 8, 13. 18 minus 13 should be 5, and it is. Okay. So that's how you do it, and that should be real straightforward. Let's look at the next one. So 4. Okay, so we're going to multiply these. So remember, you just copy this partial product. We'll let this be the multiplicand. This will be the multiplier. So that's really easy. Maybe we'll do this a little bit. Let's see. So we'll take 1, 0, 0, 1, and we're going to multiply it by 1, 1, 1, 0, 0, 0, 1. 1, 1, 1, 0, 0, 0, 1. All right. So the first one, we copy this, 1, 0, 0, 1. Then we copy just zeros. Then we copy just zeros again, shifting each time. Copy zeros again. And then we're going to copy this 3 times. 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. Now we're going to add all this up. So maybe I'll put in all the rest of the zeros. Trying to keep it lined up a little better. Okay, so that's going to be a 1, a 0, a 0. That's going to be a 1, a 1, a 1, a 1, a 1, a 1, and a 1. So that's the answer. A lot of 1s. So this is actually 9 times whatever this is, which is 1, 2, 4, 8, 16, 32, 64. So 16, 32, 64. So plus a 1. So that's going to be 20 plus 30 and 60, or that's going to be, 20 plus 30. So it's going to be 20 plus 60, so that's 80 plus 32. That's 102. No, 112, I guess. Yeah, because 80 plus 32, yeah, 112. And then we add 1, so that's 113. So 9 times 113, that's a big number. Yeah, so let me do it. Calc. Okay, we'll do this, and we'll let's see. Yeah, we'll squeeze it right in here. All right, so we'll do, and let's do, if we do the scientific, I think actually we can even do the computer graphic programmer, this one. Okay, so let's put in 9 times 13. 9 times 113, 113 equals 1017. Okay, and then in binary that would be 1001 111111. So 1001, then 111111. All right, so that's correct. And in hex, it would also be 3F9 in hex. So this would be 3F9, base 16, is their base 10. Okay, so it checked. So we did it right. All right, continuing here. Oh, it kicked me out. So that was 3. Oh, there we are. So no, that was 4. And then 5. Let's see. Divide this. I'm not going to do the division. If you screw that one up, it's on you. It's too much work. And then, oh, did another one. Just by shifting the dividend. Okay, so here, so when you have a power of 2 that you're dividing by, you can do it by shifting. So all we have to do is shift 1, 2, 3, 4 times to the left, and we will have divided it by, in this case, 8. So 1, 2, so well, divide by 2, 4, well, shift 1, 2, 3. So that's dividing it by 8, I think. Well, if we shift once, it's divided by 2. Shift twice, it's divided by 4. Shift 3 times, it's divided by 8. Yeah. So we only have to shift 1, 2, 3. So the answer should be 1001. Okay, so let's see what this is. That is 1, 2, 4, 8. 8, 16, 32, 64. 8 plus 64, so that's 72. And 72 is being divided by 8. So 8 into 72 should be, 9 times, right? Make sure I get it right. So 72 divided by 8 equals 9. Okay, so our final answer should be 9. And yeah, so what we do is we shift 1, 2, 3 times, and that gives us 9. 1001 is 9. All right, and then that's 6 and 7. Turn 75 into a binary number, and then take the 2's complement in 8 bits. So the first question is, will 75 as a 2's complement fit into 8 bits? Well, remember, in 8 bits, we can have a number as big as plus 127 and as small as minus 128. So yes, it'll fit. All right. So then all we have to do is turn 75 into a binary number and take the complement. I'm going to leave that one for you guys to do. Let's look at 8. 2's complement is used more than ones or sign in magnitude for negative numbers in digital devices because it has 2 representations for 0. Well, okay. So which one of these does 2's complement have 2 representations for 0? I'm skeptical of that, right? Probably not. So we want to pick the answer. So that doesn't sound right, but I'm not going to tell you for sure. All right, and then 9. When we do unsigned math, we should pay attention to the carry out, since that will indicate an overflow. All right, so remember what we said. When we do signed math, we ignore the carry out. So if you ignore the carry out, not a problem. So when you do unsigned math, can you still ignore the carry out? I'll leave that for you. And then 10. Many microprocessors use a special V status bit. This is set when you have 2's complement. When you have a 2's complement overflow. The definition of 2's complement overflow is that if you add 2 positives and get a negative result, or 2 negatives and get a positive result, you have overflowed, and that you can't overflow if you add 2 addends that are opposite signs. Okay, we talked about that specifically. I'm going to leave that one for you too. Okay, I think with that we're gonna call it good. So I'm going to sign off. We will then see you Monday. I will do a live Zoom on Monday, and hopefully next week will be our last week on Zoom. Hopefully I'll be there for you on Friday live on Zoom, but I may have to do the same thing next week. But obviously when we have class, I'm just going to have to miss the start of my Micro 1 lab. But that's how they set the thing up. So, all right. With that, I'm going to stop, post this video, and we will talk to you later.